Okay, so in last class we have covered all these rules, that is Hebbian, perceptron, then Woodruff, delta, correlation, and Vinerti call, along with its associated rule out star. Then we have revised in brief what these rules are and what are their requirements. Say what should be their initial value, weight values. Are they supervised, unsupervised, and so on? Are they applicable to layers like this, or they are applicable to a neuron? Now today we are going to see some problems based on the earlier theory. I hope that will help you to understand the things in more depth. Now the problem here is it's an analog to digital converter using, say, perceptron, and can be used for coding a continuous valued input X into 4-bit unipolar binary code. So binary code is O0, O1, O2, O3. So this code is generated for given input. So this is like your ADC circuit. I will show you that circuit. So output is of the form from 0, 0, 0, 0 to 1, 1, 1. Okay, that is 0 to F. And the input is assumed to be in the range -1 to +60. And neurons are, remember, binary unipolar neurons. It means that output is 0. See the condition when net value is less than equal to 0. Output is 1 when your net value is more than 0. So this is the thing you should remember. Now this is the circuit which I was telling you about, that is ADC. Now here you are supplying some input and codes are generated here. Suppose you apply 0 volt, then you are expecting it should give you 0, 0, 0 as your output code. When you apply full voltage, let us say if you apply some 16 volts over here, then it should produce 1, 1, 1. So that is the output in the form of digital numbers when you supply input. So whenever your input is of this form, corresponding codes are created here from 0, 0, 0, 0 to 1, 1, 1, 1. Okay, so that is how this circuit should give you. Now our task here is to verify this concept or ADC, and we have to find out to what range of input volt these different codes are generated. Say for example, if I say code 0, 0, 0, 0, for what range of input this is produced. Say code 0, 0, 0, 0, 0, 1, what range of input is required. So how to find out this thing? And first of all, we have to check whether this is doing this, and then we can proceed further. Now to solve this problem, we can start from bottom. We will see what these individual neurons, say lying over here, they are doing. So this is the set of neurons. There are 4 such neurons, one for each bit. This is 0th bit and this is MSB 4th bit. Now if you see, say this 4th one, that is output 3, what it is receiving? It is receiving X from here, then minus 7.5 from here. So this is a thresholding terminal. So what I receive at this point is x minus 7.5. Okay, and output O3 is a function of x minus 7.5. Now when you go to the third neuron, this one, what you see is it is receiving some input x, same input, so x, then there is one more term coming from the fourth neuron, that is minus 8 into O3. So threshold here is 3.5, so minus 3.5 minus 8 O3. So this is the net value for this particular neuron. So here output will be, say, O2 is a function of x minus 3.5 minus 8 O3. Okay, so like that, when you go to the second one, you can see that x1 is appearing here, same input is going here, minus 1.5. Okay, then two more things are appearing here. One is this one, the other one is here. So it is minus 4 O2, then minus 8 O3. Is that right? Okay. So this is the net, you can say, going to this particular neuron. And obviously output O2 is a function of x minus 1.5 minus 4O2 minus 8O3. Now go to the first one, that is 0th position. Same x is again going here. Remember, input is same for all four neurons. So again, here it is x minus 0.5. Now you see one more input is going here. It is minus 2O1 minus 4O2 minus 8O3. So this is the net value here, and output O0 is a function of this x minus 0.5 minus 2O1 minus 4O2 minus 8O3. Okay, so if I write cleanly, so this is the implementation. So there are four equations implemented here by individual say neuron, say one equation per neuron. So this is implementation for each neuron. Now suppose my input is let us say 0, assuming that all O1 to O3, O0 to O3 are suppose 0. See what happens. Now suppose my input is 0, then this will be 0 minus 7.5, so which is less than 0. So output transferred here on this line is 0. Now when you go to this particular neuron, since O3 is 0, so this term will be 0. So what is implementation now? Because O3 is 0, it is x minus 3.5. Output is a function of x minus 3.5. Since my input is 0, which is less than 3.5, this will also transmit 0. Okay. Now go to this second neuron. Here implementation will be now changed to this, because of O2 is 0 and O3 is also 0. So it is x minus 1.5. So here output is function of x minus 1.5. Since my input is suppose 0, then this is less than 1.5. So this will also transmit code 0. Now come to the first neuron, that is 0th position. You can see this is 0, this is 0, and this is also 0. So these are all zeros. So what finally implemented is x minus 0.5. Since my input is suppose 0, then you can say that 0 is less than 0.5, so this will also transmit 0. So you can see for 0 volt as your input, the code generated O3, O2, O1, O0 all are 0. Okay, so this is fine. That is what I expect. Now question is up to what level this code is maintained. Now you can see what happens if my input is suppose 1 point, let us say 55 volts. For this 1.55, let us check what happens. Say x is here 1.55. So this 1.55 is given to everybody. So here 1.5 will come. If you compare with 7.5, this is less. So again 0 will be transmitted. So if this is 0, this will be also 0. So this is 1.5 minus 3.5, which is less than 0. So again you will transmit 0. Now when you come to this position, so this will be 0 here, 0 here. So this is 1.55 minus 1.5. Now there is some net value which is more than 0. So this is going to get, I think, fire. Am I right? Okay, so this is going to get fire. Now if this is fired, what will happen? The O1 is now 1. Okay, and these two are 0. So what is net implementation? Net implementation here is x minus 0.5 minus 2. Okay, so minus 2. So it will be x minus 2.5. Since now, since this is 1.55 minus 2.5, this is less than 0. So here I will transmit 0. So what is equivalent binary here? 0, 1, 0, 0. So this is representation of, say, 2 in our case. So initially I said if my input is 0, then I was getting a code 0, 0. When I put there 1.55, you will see that I received 0, 0, 1, 0. So for different input range, for different input voltage, there will be a different code, and for certain range of inputs, this code will be maintained. Okay, so for 0 there will be some range, for 1 there will be some say I should say 0 code, there will be one range. For 0, 0, 1, there will be one range. 0, 0, 1, 0, there will be one range. Now what you have to do is you have to find out for each port what is the voltage for which this code is transmitted. Say for one, I have found out suppose 1.5. If it is 1.55, then you will go to this code. Now for 0011, can you find out the voltage? So try to complete this table on your own. If you have any doubt, you can ask me. Otherwise, I will move to the next problem. Anybody with doubt? Okay, so next problem is problem 2. The feed-forward network shown using bipolar binary neurons. Okay, so here the neurons are bipolar binary, so outputs are +1 or -1 depending on the net sign. If net is say less than 0, it will produce -1. If net is suppose greater than, not even equal to, I should say greater than, then it will produce +1. Okay, so this is bipolar binary. I can add, if I require here, equal sign. So depending on my choice. Suppose this is with greater than or equal to sign. Now is mapping the entire plane x1, x2 into a binary value. Find the segment of x1, x2 plane for which O4, this final O4 produces +1, and its complement for which O4 is -1. So we have to find out on the plane x1, x2, where is the region where this last neuron will fire. So why it is x1, x2? Because we have two variables, x1 and x2, as our inputs. So these are our inputs, and this is the thresholding terminal. Now to solve this problem, we can observe from the last end. We are expecting that suppose this should be +1. Okay, I want that this should be +1. Then when this can happen? So this can happen only when the net value here is positive. If net value is positive, then and then this will happen. Now to make this positive, you can observe that this O1, the output of previous neuron, O1, O2, O3, they are coming with importance 1, 1, 1 here, and 2.5 is subtracted from that. So what is net implementation here is O1 plus O2 plus O3 minus 2.5. Okay, so this is my O4. Now to make the thing clear, I can say that this fourth neuron will fire only when this net is more than 0, and when this will happen, whenever this is 1, 1, 1, that will be giving you some 3 minus 2.5, then and then this is going to produce or fire result +1. Now if any one of these neurons, previous neurons, is producing -1, so what will happen? So this will be giving you some 1 minus 2.5. Then this will be a negative number, so this will not fire. Suppose this is +1, this is -1, still it will not fire. Say this is -1, this is -1, this is -1. then there is no question of firing at all. So for any combination, this will not fire. It will fire only when all these outputs are +1 here, +1 here, and +1 here. Otherwise, it will not fire. Now our task is to find out the region in x1, x2 plane where these 3 neurons will get fire at a time. Now to do that, what we do? We find out what these individual neurons are doing. Okay, we have found out the last neuron is doing this thing. It is implementing O1 plus O2 plus O3 minus 2.5. So this is last neuron. Now we will go to the previous layer. So this layer is receiving x1. The first neuron is receiving x1 multiplied by -1. So this will be minus x1. It is receiving x2 multiplied by 1. So plus x2. Okay, so this is, I think, there is no further connection. So this is x1 minus x1 plus x2. So this is the net value, and function of this will produce output O1. Now when I go to the second neuron, you can see it is 2x1 minus x2 minus 1 multiplied by -3, so plus 3. Am I right? Function of that will give you output O2. Now when you go to the third one is receiving -3 into x1. Nothing is received. Only this is the terminal here. So function of that is my O3. Okay, so 3 neurons, 3 previous layer neurons are implementing these 3 functions. Okay, now let us plot what they are doing on x1, x2 plane. So if you see, the first neuron is implementing minus x1 plus x2 equal to 0. So if I plot this particular line, it is this one. Okay, so you can actually see that this implementation is nothing but x1 equal to x2 line. So this line this particular line is x1 equal to x2, or x1 minus x1 plus x2 equal to 0. Now which side of this line will give you positive response? That is the question. When it will give you, so let me, I think I should rub this thing. Just 1 second. Okay, then I think better. So if I take the first line, it's getting a little difficult here, but let me try this. It's not coming fine. should pass through 0. Okay, something like this. This is not perfect. It is minus x1 plus x2 is equal to 0. Okay. Now, when this neuron will fire? So there is a simple trick you should remember. This is the line implemented by this particular neuron. So whenever this particular sum is more than 0, this neuron is going to fire, and whenever this particular sum is less than 0, this neuron will not fire. So this thing you should keep in mind. And to know which is the region for a given neuron that will produce positive response, it's very simple. What you do is collect the coefficients of this line for the variable. Say for variable number 1, I have this coefficient as -1, and for variable 2, I have the coefficient +1. Now this is the vector direction for which this particular line will produce positive response. You can try and put some values here, and then you can check. Now where is this direction? Say this is, suppose 1, this is -1, say this is 1, and this is, say, -1, and this is 0. So -1, so this is -1 +1. So this is the direction of my vector. So this direction. So this direction is actually perpendicular to the line. So this -1 +1, that is this side of this line is positive and this side of this line is negative. You can check for any point above this line and put that value here. Suppose I take a point here, suppose -2, and say this is the point 1. I take a point -2 and 1 and substitute here. So it is minus of -2 plus 1. So this will be 2 plus 1, so that is 3. So this is a positive number, so neuron will get fired. Now suppose I put here some number, some point, say let us say 2 and 1, say this one. Suppose I put here 2, 1, which is the point this side of the line. So 2, 1 will give you -2 plus 1. So net value is negative. So your neuron will not fire. Now remember, we will see more things, detailed things on this when I will tell you perceptron learning in detail in next chapter. Time being, you just remember that collect the coefficients of the line variables that will give you the direction where neuron will fire. Okay, now similarly, when I take the second neuron, it is implementing the line 2x1 minus x2 plus 3. So where is this line? Suppose I want to plot this line, put x1 equal to 0. Suppose I put here x1 equal to 0. So x2 is 3, somewhere here 3. And when I put x2 equal to 0, x2 equal to 0, so it will be minus 3 by 2. So somewhere here. So that is the intersection point. If you join these two lines, since I am not drawn properly, you will get some line like this. Okay, so this is neuron number 2, and this is neuron number 1. Now where is the positive region for this particular line? So again, collect the coefficients of line. So collect the coefficients will result into 2 minus 1. So 2 minus 1, where is this direction? So 2 minus 1, so 2 and minus 1 somewhere here. So this particular direction. So for second neuron to get fire, you must be this side of the line. Okay. So to get fire, you should be this side of the line. And for first neuron, you should be above this line. So to make the thing fire, that both neurons, suppose I want to get fire at a time, then you must satisfy these two conditions. You must be this side of the line, number 2, and you must be above this position or above this line for neuron number 1. And this will be the region where both neurons will fire. Now that is not enough for me, because what I want 3 neurons to get fire at a time. Now the third one is saying minus 3x1, implementation is minus 3x1. Okay, so where is this line? Can you tell me where is this line? So simple, you collect the coefficients. Which side of the line is this one? So this is minus 3, 0. So where is this? Minus 3 and 0. So this is the direction where this particular neuron will fire, and perpendicular to that is this particular line. So this is neuron number 3. And question was where this fourth neuron will fire. That means I have to fire all the 3 neurons. So the common region is this one. Okay, so this is the common region. Say from here to here. Okay. In this region, if you put, or if you take any point from this region, all 3 neurons will fire. If all 3 neurons are getting fire, that means the sum is 1 plus 1 plus 1, and threshold was, I think, 2.5. You can check here. Threshold was right 2.5. So 3 minus 2.5, and it is greater than 0. So this will produce plus 1. Now for any other point, say point here or here or here, any other point, 3 neurons will not fire at a time. So your output will be negative. So what I can say is this shaded region is class 1, and rest all the plane is class 2, where output is minus 1 and here output is plus 1. Okay. Now next problem is the network shown in figure uses neurons with continuous activation function. So activation function here is continuous with lambda equal to 1. So it is talking about that sigmoid function, and it is given like this. So this is a bipolar actually, since we have output in the range -1 to +1. The neuron output has been measured as O1 is 0.28, so here it is 0.28, and O2 is -0.73. Find the input vector x. So that is the question. Find out input for which the output produced is like this, that has been applied to the network. So also find the slope values of activation functions at activation net1 and net2. So they are asking you to find out f dash of this. Okay, now activation function is this one. So what we can do here is, you know that we have this activation function. So this 0.28 is equal to, for first neuron, 2 divided by 1 plus e to the power minus net 1 minus 1. Okay, and for the second neuron it is minus 0.732 divided by 1 plus e to the power minus net 2 minus 1. Okay, so these are two equations for neuron 1 and for neuron 2. So if you simplify, so this one will go here, and then you can further simplify this and bring this thing to left hand side and the other things to right hand side, and take log of this. Okay, so take log of this will give you what is net value. Similarly, for second neuron, you take this -1 to left hand side, then you rearrange for net 2 like this, and then take log. So you have two equations now. So if you take now net 1, so this is net 1 equal to, and this is net 2 equal. So after taking that log, so this will be minus 0.57 and plus 0.57 and minus 1.86. So these are, say, equations, so 1 dash I can say, and 2 dash. Now what we want here is what is x1, x2. So we have two equations and two unknown variables, so we can easily find out. So you can take these two equations, okay, then you can just do the arrangement as usual. So divide by 4 to equation number, say, 1 divided by 4, you just subtract and you will get the answer for x2. So if you get answer for x2, you can substitute back for x1 and you will get these two numbers. So input x is 0.315 and minus 2.2. You can verify this answer. So this is how we backtrack what given the output of neuron, what is input of that neuron. So I will stop here. If you have any doubt, you can ask in next class, that is after the exam class. So on Tuesday we will have test, and I have already given you assignment that you should submit before that exam on Monday. So it will give you good practice of exam on Tuesday. So Tuesday's exam will be similar to your assignment. So hope you will solve. If you have any doubt, you can ask.
Sir,
Yes.
sir, there is a doubt in assignment. In a question number two,
Hmm.
they mentioned like three parts, right? OK1 plus O to the power K2 plus K plus 2, and
Hmm.
C is another part. So should we have to make three different PITS models, or should we have to use for each one model, like for everyone has to
For each
what is
problem
it?
you solve, you take one model. Okay.
Okay, and yeah, and there is one more. They convey like there is a naming convention that O of K plus two, and so what is this means? K plus two or K K? So is that the number
That
of
is
neurons?
that is the iteration step.
Okay,
Okay.
okay. And one other thing is uh, in yeah, there is a in question number four, like backtracking the training. So we
Yeah.
have to backside means first of all we have given the B for W4.
Like that, what we have done right now, we know the output, then we are going towards input, right?
Okay,
In that case, what we have to track is what were the earlier weights. So weights are, say, delta W new is equal to delta W, say, W new is equal to W old plus delta W, right?
yes,
So delta W you have to compute, and then you have to subtract from new so that you will get old.
okay, got it.
Okay, like that you have to solve.
Yes, sir. That's all.
Is
Thank
that
you.
fine?
Yes.
Okay.
Sir, we
Ah,
have
yes.
exam.
Ah, yes.
Sir, on
Good.
14, some of us have exam.
Which exam?
TCS NQT.
14th, na?
Hmm.
What time?
2 to 5.
2 to 5. Okay.
Yes, sir.
So you can give at 6. We have to do that some arrangement for that. But then it will create a problem actually. How many of you have?
So there are three different slots. So every slot has every exam. Like,
So how these are people are keeping the things in regular classes time? For every class you are saying you have some placement activity. So they should not use this timing, right? So what is solution?
Sir, can we give another time means after 6 or something like that?
So can you shift it to Monday? Monday is holiday, na? We can shift it to Thursday. Do you have any problem? We can shift exam to Thursday. Is that fine?
Okay, sir, on
Sir, on Thursday we have exam of same NQT.
So, so what we do, we will do on 14th in the evening.
Okay, sir.
Evening what time?
After 6 for all, someone is saying.
7 o'clock?
Yes, sir, that will be fine.
Okay. So that is final.
Yes, sir.
So on same day, that is on 14th in the evening, 7 o'clock.
Yes, sir.
Okay. So inform everybody because I don't think students are there.